So with that, let's dive into the first question. Should be on the screen. So the question says that we have a circuit diagram provided. That's on the right here. Each resistor has a resistance of 10 ohms. They're labeled as R1, 2, and 3, but probably to make things easier, I'm just going to call them. Each one of them, we'll just probably give it a generic variable R just to simplify things because they are all the same. And we're told that the battery is supplying 1.5 volts. So that's this variable here, this epsilon. So epsilon is reserved usually for a few things, but in this context for electromotive force. You might also see other variables like V for voltage, delta V for voltage or potential difference, but in most of these problems, I think we have epsilon. So the question is broken down into three parts. The first is to find out what the equivalent resistance of the resistor network is. The second part is to find the current coming out of the battery, so that's just I, not I1 or I2. But then part three is to apply Kirchoff's laws and to find the current I1 that's flowing through this left branch of the resistor network. So for part A, I'm just going to quickly, before we dive in, because I think it's nice to do the result kind of generically before we need to use it. A lot of the time you have two resistors in parallel, and what you guys are given in lecture usually, if I call the first one R subscript X, this one subscript Y, what you guys are told, if you want to find the equivalent resistance, is that the reciprocal of the equivalent resistance of these two resistors is equal to the sum of their individual reciprocals. And this just comes basically out of Ohm's law, but what I find a more convenient result that I like to memorize or keep in the back of my head is to actually figure out what this is in terms of like a solve for R equivalent. So this isn't very difficult. We multiply the first fraction by R subscript Y, we multiply the second fraction by R subscript X. We get Ry plus Rx over the product of Rx, Ry. And then we can just take the reciprocal of this whole thing. And this is the result that I kind of like to remember. Because it saves you, when you're doing something like a test or whatever, it saves you from having to worry about executing both steps of this algebra if you just remember what the final answer is. I don't think that's very hard to remember. So we'll keep that in mind. Okay, so for part A, we have two branches. We have this left one where there are two resistors in series, and then we just have this right one where there's a single resistor. So the first thing we're going to find is the equivalent resistance in the left branch. So I'll call this R subscript 1, 2 to mean the equivalent resistance of resistor 1 and 2. This can get kind of confusing if there are more than 10 resistors, so you could imagine there being R12, but this is not R12, it's R1, 2. These two resistors are in series, so it's pretty straightforward. You just have R1 plus R2. If we want to find the equivalent resistance of the whole network now, I'll call that R1, 2, 3. The way we can think about this is if imagine that you combine this whole branch here into the equivalent resistance that we just found, R12, so pretend like it's one resistor at this point. And we have R12 in parallel with R3. And then we can just use this result down here that we found for when you have two resistors in parallel. So what that would end up being is R12 times R3 divided by R12 plus R3. And at this point, we can break down what each of these, we can insert what we found before for R12. So something like R1 plus R2 times R3. And then the denominator is R1 plus R2 plus R3. But remember, like I said, these are The details of the question, they told us these are all equal to 10 ohms. I'm not going to worry about the actual numbers, but since they're the same number, I said we'd call these R. So everywhere where we see R1, R2, or R3, because they have the same resistance, let's just replace that with R. So the top becomes 2R, that's what R1 plus R2 is, times R3, which is also R, so we're left with 2R squared, divided by the sum of R plus R plus R, so that's 3R. Or in other words, we're left with an equivalent resistance of 2/3 R. So that's our answer for part A. Part B wants us to find the current I. So we know what the voltage or the electromotive force of this battery is. We know what the equivalent resistance of the total circuit is. We just found that, so we can just leverage Ohm's law to figure out what this current is. So Ohm's law is V equals IR. If we want to solve that for the current, that's the potential difference of the battery divided by the resistance in this case, which is our equivalent resistance R123. And if we insert the result from part A, what we're left with is 3 epsilon, which looks kind of funny when you write it like that, divided by 2R. So that's basically just putting this answer down here. Very simple result. Okay, and lastly, we want to find out what is the current I1, and we're told to use Kirchoff's laws. And I guess what I'll say about Kirchoff's laws is that the way that I view it is Kirchoff's laws give you ways to find information about the circuit, and that's kind of where the physics is embedded. But really what it does is it gives you a set of equations or a system of equations, and you can choose how to solve them. I think you guys probably have experience by now that when you have a system of equations, usually you can go about solving it many, many ways. And Kirchhoff's laws tend to give you more equations than you have variables, so you have excess information. So the take-home message is that I might solve something one way, you might solve it another. The pieces of information that you choose to use, usually you'll end up in the right place. There are obviously some quicker routes than others, but if what I do doesn't make sense to you, that doesn't mean that that's the only way to solve it. So what I'm going to do is I'm going to use Kirchhoff's loop rule, and what you want to do every time you use Kirchhoff's loop rule is you want to, it makes it easier if you actually draw the loop. So I'm going to draw the current coming out, or I'm going to have the path start this way, follow the direction of the current that comes out of the battery, goes through junction A, and then we'll branch off into the left branch. And then we'll just make our way back to the battery. Something like this. So now let's write down the equation that we get from that. So basically what we're doing is we're going to start at the battery, we're going to go around the loop, and we're going to sum up if the potential goes up or down. And we know that kind of adding these all up, they have to sum to 0. So if you cross the battery, the potential is increased by an amount epsilon. The current is flowing kind of, we have no resistors that we encounter as we approach junction A. Once we get into this left resistor branch here, the current is flowing downwards in this direction, and it's going through resistor 1. So if the loop is also passing downwards, we're going with the direction of current. As current passes through a resistor in the direction it's naturally going, the potential drops. So hopefully that's familiar, something you guys saw in lecture when these rules were covered. So the potential decreases by an amount I1 R1. We just get that from Ohm's law. Same thing when we encounter resistor 2, the potential decreases I2 R2. And basically at this point we encounter no more batteries, no more resistors. We can close the loop, make it back to the battery. So there's no more changes in potential. Because we've done a full loop, kind of the essence of Kirchhoff's loop rule tells us that that has to sum to 0. And at this point, I think we have, oh, I made an error. I2 is the current going through the second branch. So this is still I1, it's the same current. I have a really bad habit of writing down I1, R1, just kind of keeping the subscripts the same, right? It's if you're not thinking carefully, you can sometimes write things down incorrectly. And with using these Kirchoff's laws, you want to make sure that you're writing things down very carefully. It's very helpful when you're solving systems equations. Okay, so we want to solve for I1, and I think that's all we really need to do. Thankfully, R1, R2, and epsilon are given quantities in this problem, so we don't have to actually solve any systems of equations. At this point, we are essentially done. And we could simplify this a little bit further. We can replace R1 and R2, each individually with R, and we're left with 2R. So that is our value for I1. And then really quickly, just for kind of extra bonus points, whatever we wanted to figure out what is I2, the easiest way to do this is to leverage the junction rule. So what the junction rule tells us is that the current flowing into and the current flowing out of a junction has to be conserved. So in this case, an easy way to write this down, I'll do some algebra on the fly, but I2, which is the current that comes down to the right out of junction A, is equal to I minus I1. So basically what I'm saying is I1 is flowing into the junction, I1 and I2 are flowing out of the junction, and I've done a bit of algebra to just kind of set us up for the least amount of headache. So we already found what the total current was, I. We found out what the branch was in, the amount in branch 1 was. So pretty straightforward, just epsilon over R, because we'd be left with 2 epsilon. But I think that's pretty intuitive. We already found what was found in the sky flowing into the junction. We found the first part flowing out of the junction. So basically everything that's left is it's the difference. So that's everything I think that we could possibly want to learn about this circuit. I don't think you guys have any questions in the chat, so hopefully that was clear. And we'll move on. So for question 2, what we're told is that the circuit provided here on the right, it's referred to as a Wheatstone bridge. So that's just kind of for, it's a real circuit for general interest if you want to read about it more on your own. And one of the functions is it allows us to determine the resistance of an unknown resistor, Rx, by adjusting what is referred to as a variable resistor. So that's the Rs over here. So this is actually like a physical circuit element. It has a knob on it. You can turn the knob, and it will change the resistance. So what you do is you change this resistance Rs until the voltmeter, which is in the center of the circuit here, reading across terminals A and B, until it measures a potential difference of 0. And we can use that to figure out what Rx is. And what we're given is a particular set of parameters. We're told what R1, R2, and what you have to turn the potentiometer to, the variable resistor, to get that potential difference to be 0. So with all that in mind, we now want to figure out what is this unknown resistor Rx. And it's not explicitly stated here, but we're going to have to use Kirchoff's laws. So just to kind of illustrate the total quantity of information you can get, let's write down basically everything we can from Kirchoff's laws, and then decide which equations we actually want to use. So I'm going to start, because they're generally a little bit simpler, with the junction rule. I guess before we start, we need to pick some currents. So I'm going to follow kind of the convention of the previous problems coming out of the battery. Remember, this is a positive terminal, this is a negative terminal. I'm just going to have a total current I. And when it reaches this top junction here, I'm going to say it splits into 2. We have I1 traveling down the left branch. We have I2 traveling down the right branch. And they both continue. They meet up again at the bottom, and they recombine, and we have, yet again, we have I traveling back into the negative terminal of the battery. So yeah, with that in mind, we kind of even spoke about it. We can write down, actually maybe I'll switch to black and we'll reserve blue for drawing the diagram. So we have the junction rule. The first junction that we encounter is right here. And kind of conservation of current is all this is really a statement of. We have I going into the junction. We have I1 and I2 going out of the junction. If I drew the arrows in any different direction, then there's no reason for me to, I think it's pretty intuitive. I think it follows good logic that if I've drawn I in the direction I've drawn it, based on what the battery polarity is, that I1 and I2 will go the way they do. I didn't have to draw it that way. I could have said I1 goes this way. All that would happen is if you draw something the wrong way, the numbers will come out negative. So right now, if all of my directions are correct, then I1, and I2 should all be positive. If you run into a negative, that means when you get to the very end of the problem, solve everything normally, but then go back to correct your diagram and switch the directions as needed. So this is what we learned from the junction rule. You could make the argument, maybe we could write down an equation for this junction down here at the bottom, but I think it's pretty clear to see that if you wrote that down, it would be the exact same as the information we already have here. So there's no sense in writing it twice. Okay, so now we want to get the equations that come out of the loop rule. So we need to draw some loops. So there's 3 loops that we can draw here, and I'll draw all 3 and I'll write down the equations, but I think what you guys will appreciate or realize is that 2 of them can be combined to make the 3rd. This is usually the trick with a lot of these Kirchoff's law problems, is not getting overwhelmed with too much information or confusing. So the first one I've drawn as is, I've used kind of the outside of the loop. I've drawn it in blue. It's the path that follows kind of the current capital I from the battery, and then goes through the I1 branch of the Wheatstone bridge. We can do a second loop. We'll go in the same rotational direction. And it's pretty similar, but we'll just go through the I2 branch of the Wheatstone bridge. And lastly, I don't think it really matters which way we go, clockwise or counterclockwise, but we can do one that does something like this. There's a loop here, so we can go through it that way. And if you want to go in the other direction, it doesn't matter. Like I said, just the signs will change. Okay. So from the first loop, we start at the battery. Potential increases by some amount epsilon. Then we reach our junction. First resistor we encounter is I1. Potential drops by I1, R1. Next we encounter RS. Potential drops I1, RS. And then we encounter no more resistors or batteries until we make it back to the start of the loop. So that's the first loop. Second loop, pretty similar. Remember, it's this one on the inside here. We're going through the right branch of the Wheatstone bridge. So we first encounter I2 going through R2. Next, we encounter I2 going through this unknown resistor Rx. And we don't encounter any more elements that change the potential before we make it back to the battery. Lastly, we can, if we start kind of at the beginning here, as I've drawn this, we can do the inner loop of this. So we're following I1, given the direction we're going around this loop. So the potential will drop by some amount I1, R1. Drop again, I1, RS. Then it will increase. So the reason this increases is because the potential is, the current I2, when it reaches Rx, it's moving kind of down and to the left. We're going up and to the right. So you can imagine that the potential, we'll maybe switch to red just to be consistent. Potential was higher here before the current went through the resistor, then the current went through the resistor, and it's minus here. So it's kind of like a polarity, positive, negative. So if we're going against that with the direction that we're going around this loop, then the potential is actually going to rise. We're going from negative to positive. And same story with R2 here. And I think it should, hopefully, maybe you guys need to just quickly do the addition or subtraction on your own. But if I called this equation 1, this equation 2, and this equation 3. Hopefully it will be pretty clear, I think, that 3 is equal to equation 1, oops, minus equation 2. So I wrote down equation 3 just so we could have all the information we want to work with, but it doesn't provide us with anything new that we didn't already have with equations 1 and 2. Okay, so this is everything that we can obtain from Kirchhoff's laws. There is a little bit of extra information that's pretty critical to solving this. So I think the point of this question is to not autopilot and just go write down these Kirchhoff's laws and start solving things, because there's a little bit more information that we need before we can proceed. So I'm gonna, I'm gonna erase this really quickly just to tidy things up so we can see what we're talking about. So the other thing is in the operation of the Wheatstone bridge to find an unknown resistance, what we're told is the potential difference from A to B is 0. So what this means is that the potential difference at the halfway point, if you want to think about it this way, of the right branch is the same as the left branch. So if these two are equipotential, A and B, that's what that means when there's no potential difference. That means that the potential drop, I still want my currents, I regret. Getting rid of these, this is I1, this is I2. So because these two, you can consider that Rx is in parallel with Rs, right? They're not in series. They're both connected to this point here in parallel. The negative side of both of these resistors, once the potential is dropped, is at the same potential as the battery negative terminal. The positive side of both these resistors is at the same potential. That's what it's meant by VAB is equal to 0 volts. So what this means is the potential drop across both those resistors is the same. So we'll call this extra information. And this all comes about from the fact that VAB is equal to 0. So this tells us that I1RS, that's the potential drop across resistor S, is equal to I2RX. And similarly, if we wanted to do the same analysis for the upper half of the Wheatstone bridge, the same arguments can be made. So we'd similarly have I1R1 is equal to I2R2. And this is only the case, I can't stress this enough, this is only the case when this is true. So this resistor, this potentiometer that you're playing around with RS, imagine you're in the lab, you're turning a dial on it. If you have not reached 0 volts, equal potential at A and B as measured by the voltmeter, this analysis doesn't work. So it only works when when VAB is equal to 0. But with that in mind, now we have all the information that we can that we can work with. And I think what you would find if you just started working with the junction and the loop rule and you didn't have this extra information, you would kind of go in circles. You would not have a way to get rid of enough variables to get exactly what you want. Okay, so the first thing I want to do, we'll take equation 1, and I'll solve that for I1. So that's equal to epsilon divided by R1 plus RS. So what I've done is I've factored out the I1, I've moved everything to the right side and divided by R1 plus RS. Similarly with equation 2, we can solve for I2. And the form is nearly identical. But this time it's R2 plus RX. And what we're going to do now is we'll take each of these, and if we call it this first kind of extra equation, we'll call it star. What do? We'll put 1 and 2, and we're going to put them into equation star. So where we had I1, we will substitute epsilon divided by R1 plus RS, R1. Where we had I2, we will put epsilon divided by R2 plus Rx. And now we just need to solve for, oh, that was not R2, that was Rx. Yes, now we just need to work through the algebra and solve for Rx. So we have an epsilon on both sides. Those will go away. We have R1 divided by R1 plus Rs. That equals Rx divided by R2 plus Rx. So the real thing that bothers me here is that we have kind of an Rx on both sides of the fraction, or on both the top and the bottom. But if we take the reciprocal of the whole thing, we can get rid of them. So this becomes R1 plus Rs divided by R1. It's the reciprocal of the left side. The reciprocal of the right side becomes R2 plus Rx divided by Rx. Now we have the first term here is R1 over R1, so that's 1 plus Rs over R1. We have something similar on the right side. We have 1 plus R2 over Rx. I've gotten rid of the Rx over Rx now. The 1's cross off. So now we have a term that just looks like this. Rs over R1 equals R2 over Rx. What we want to solve for is Rx, and I think that's pretty simple with what's left. It just equals R2 times R1 over Rs. So pretty simple ratio, which is a cool result when you look at like a, I don't know, a fairly complicated circuit. You can imagine how this exact experiment might be pretty helpful for figuring out what an unknown resistance is if you didn't have an ohm meter or something like that at hand. Okay, so I think this is the last question we have. We'll just double check. You guys are still, the pair of you that are here, still kind of quiet in chat, which is fine. I hope that means that everything's good. And we can move on to this last one. So we just have another resistor network here. We have a couple extra batteries, which sort of don't really overcomplicate things, but it's just an added nuance. So we're supposed to consider the circuit below. We have R2, which is 3 kilo ohms, R3, which is 5 kilo ohms, and then we have 3 batteries with 5, 9, and 12 volts each. And we're supposed to determine the, it says absolute current passing through battery E1. So let's quickly label a couple of the currents. So exiting kind of the positive terminal of the first battery, I'll just call this I1, keep the subscript pretty consistent. That reaches this junction here. We'll split into I2 and I3. And then obviously those recombine at this bottom junction here into I1, and then they return to the battery. One thing that's interesting to note that we'll just need to keep track of while we're working through this is notice the polarity of these two batteries are reversed. So this E2 or epsilon 2 and this epsilon 3 are just in the other direction, or in opposite directions of each other. So let's proceed basically identically like we did last time. Let's write down the information we get from Kirchoff's laws. From the junction rule, we pretty much, it's the same as last time. We have one junction at the top here, one junction at the bottom, but the information they give us is the exact same. So simply we have I1 is equal to I2 plus I3. And we can make a couple loops. And I think, again, we'll have the same scenario where we have 3 loops, but only 2 of them really are unique. So the first one that we can make is starting at the first battery and going down the branch that has R2 and the second battery. We can also start at the first battery, go around a larger loop that goes around the right branch, and lastly, and I should put arrows on these so we know which way we're going. And lastly, we'll do one that goes like this. Oops. Okay, and again, the directions don't really matter. You just need to be aware of whether the potential is going up or down. Maybe you have a current that comes out negative. It just means one of the red arrows is wrong, but the blue arrows never determine anything. The way you go around a loop, the direction doesn't matter as long as you write down the potential drops and increases correctly. Okay, so for the first loop, which went down the branch with R2 and the second battery, let's write down the loop rule for that. So we start with epsilon 1. Then we encounter resistor 2, so the potential drops I2, R2. Then we encounter the battery epsilon 2, and we're going from the positive side to the negative side. So the potential will drop an amount epsilon 2, and then we can close the loop. For the second loop that I drew, again, we started at epsilon 1. This time the first thing we encounter is resistor 3. Potential drops I3, R3. Next we encounter the third battery, and I drew these wrong. Let's correct that. The little terminal is always the minus, the big one is the positive. So we're going from minus to positive. So that means the potential increases. And then we just make it back to the battery. And lastly, we can the information is not new, but it's good to practice. So we can do this other loop that I had between the two branches that excludes epsilon 1 entirely. So we have minus I2, R2, minus epsilon 2, minus epsilon 3, minus I3, R3, plus I3, R3. Again, this is a plus because we're moving in a direction in this loop opposite the direction of the current. And I don't think we have any extra information this time that we need to worry about, so this problem is a little more straightforward. So we want to figure out what is the current passing through battery 1. So this is I1, which is the one we want to get a handle on. So what we can do is we can use we label things similarly to the last problem. We can use the first two equations we got from the loop rule and solve for the currents I1 and I2, I2 and I3, and then we can put them into our equation from the junction rule to figure out what I1 is. So equation, we can pretty straightforward see that I2 is just equal to epsilon 1 minus epsilon 2 divided by R2 from equation 2. We can do basically the identical process, and we find that I3 is equal to epsilon 1 plus epsilon 3 divided by R3. Next we want to take equation star and put in our two results that we just found. So I1 is equal to I2 plus I3, so what that amounts to is epsilon 1 minus epsilon 2 over R2 plus epsilon 1 minus epsilon 3 divided by R3. So this is where we could stop and say this is the final answer. So I guess at the very least I'll box it off. But what I'm going to do is I'm just going to, I normally don't do this, but I think it's useful at this point to put some of the numbers in because of this minus sign right here. So you can imagine if you look at the first loop that we drew, it was this one right here. On the inside that goes around, you have epsilon 1, epsilon 2, and R2. So if you just look at this loop in isolation, it looks like the battery epsilon 2 is going to be providing a current, because current comes out of the positive terminal, that fights with epsilon 1. Whichever one has a bigger voltage or potential difference is going to win. So if you notice that epsilon 1 is 5 volts and epsilon 2 is 9 volts, this actually means that what we've drawn for I2 might be the wrong direction. It's okay because what we're worried about is I1, but we should kind of figure out if the whole thing comes out positive. I forgot that this is a plus sign right here. But yeah, we should figure out if this whole thing comes out positive, is basically what I'm getting at. And then we can correct our diagram if we need to. So what were we saying? Epsilon 1 is 5 volts. Epsilon 2 is 9 volts. And if you can kind of keep a grasp of what these terms are, this first term was I2. If you see 5 minus 9, you know the first term's going to come out negative. So what this means, and we're not, like I said, we're not really concerned with I2, but we could fix this if we wanted to. And we could say that I2 goes up. But what we really want to know about is I1. So 5 volts minus 9 volts, the second resistor, or R2, was 3 kiloohms. Epsilon 1 again was 5 volts. I think epsilon 3 was 12 volts. And R3 was 5 kiloohms. So it's really handy. You guys may want to remember volts divided by kiloohms is equal to milliamps. So I'm going to leverage that now. I'm just going to kind of dump the units at the end and just work with pure numbers. So 5 minus or 9 is minus 4 divided by 3. 5 plus 12 is 17 divided by 5. We have this, and we'll just say that the units are at the end. So it's really quickly, I think it's obvious that, maybe it's not, yeah, it should be obvious, that 17 over 5 is bigger than 4 over 3, so this whole thing will come out positive, but just to verify that, let's put them over a common denominator. So 17 times 3, I believe, is 51 divided by 15, and 12 times 5 is 20 divided by 15. So we get an answer, I don't know what the decimal version of it is, we get 31 over 15 milliamps, or roughly speaking, that's 2 milliamps as a final answer. So it does mean that this number came out positive, I1 is positive, so we don't have to go back and correct in our drawing. And again, this was asking for the absolute current, so it was trying to give us a bit of an escape rope, because we didn't, if this is minus or plus, it wouldn't really matter. So I'm just giving you more advice on terms of how to make sense of the answers you're getting. So I left a blank page here. I think this is all I have for tonight. If you guys have any questions, I can hang around for a bit. Yeah, so I think that's just kind of what the absolute current is kind of like, imagine that the current is a vector, where a positive and negative might imply a direction. The absolute current just means you can ignore the direction, more or less, of the vector. It's kind of like asking for the magnitude of the current. The context in which current can be a vector is kind of weird, so saying the magnitude of current doesn't always apply, but that's how you can interpret like absolute current in this sense. So I guess what this is getting at, like if you saw something like this on a test, and if you had defined your loops differently, like if somehow you forgot how a battery worked and you defined I1 going this way, your final answer would be I1 is equal to approximately minus 2 milliamps. So what this is getting at is you can ignore the plus or minus. You don't need the plus or minus to get the answer right. You would just take the 2 milliamps. So it is removing when it says absolute current, it actually is removing an element of complexity and making your life a bit easier. Cool, I'm glad you enjoyed it. Oh yeah, another question. Can I explain the third loop in question 2? Yeah, sure. So we can tidy. Actually, I think this is fine to leave these as is. So the cool thing about Kirchhoff's loop rule is that as long as you can um, form a closed path that starts and ends at the same position, it counts as a loop. So I think the first couple ones were obvious, right? I started here, left the battery, and went either down the left or the right branch of this square or this diamond. But you don't have to include this battery, right? It's not the only closed loop that you can find. So you could have done one like this that went around the first one, or you could have gone around this diamond, this square in a counterclockwise manner. If you don't like the look of that, you can go around this way. Really doesn't matter. But to walk through it in terms of, I think the more complicated detail is um, picking out the drops. So let's go through that really carefully because I'm sure that's what you're getting at. So let's start here. We will also end there, but it kind of gives us a fixed reference point. So the general rule, if you just want to remember how to get the correct numbers, and the physics is a little bit over detailed. Basically, if you're moving in the same direction of the current, when you go through a resistor, the potential will drop. If you're moving in the opposite direction, the potential will go up. That's a really fast and easy rule if you want to remember it. So we start here. You could imagine we're moving down here. We encounter this resistor. We're moving in the same direction as I1. The potential will drop. That's what the negative's for. So we have I1, R1. Same thing. We can keep going. We turn the corner and we hit RS. We're moving in the same direction as I1 still. So there's a potential drop I1, RS. When we encounter this bottom here, we said we're going to follow the loop back up. This time we encounter Rx. This time we're moving in the opposite direction as I2. So if you follow the little rule I just mentioned, potential goes up. And we do the same thing. We encounter R2. We're moving in the opposite direction of the current that flows through R2. Potential is going to go up. I2, R2. And we're done. So we're kind of back at the start. So I think the big thing that a lot of people assume, or I found in students over the years, is they assume that this loop has to, like, the default circuit arrangement is you have one battery and a collection of resistors. And I think a lot of them assume that you have to include the battery in your loops, and you don't at all. So that's the biggest difference. Hopefully that was helpful. Cool. Glad you got it. Oh yeah, like when there's no battery there, it's weird to think of potential drops happening. I agree. Yeah. Cool. Well, there's no more questions, guys. Thanks for attending. I do appreciate the live audience, so it's great to have at least a couple of you here to interact with. Other than that, I think I'll possibly take off if